Good morning, everyone. At least morning here in Colorado. I would say beautiful Colorado because it's usually beautiful. Today's a little on the darker side, but that's all right. Wherever you are at, whether it's morning, evening, or you're watching a recording, thank you for joining us and joining me. This is a webinar on using AFT Fathom for utility and offsite engineers, where we're going to learn how to properly design for system expansions. Fire safety systems, those will be the two examples we go through. My name is Walt Prentice. I'm a business applications engineer here at AFT, which means I do a little bit of everything, but enough about me, you're here for the content. So let's go ahead and jump in. So we're gonna go through some background on unique aspects that a utility and offsite engineer has. Then we're going to dive into AFT Fathom, which is our modeling software, with specific examples. We're going to look at a cooling water loop expansion, so an expansion project, and then a Firewater system study where we're looking at an aged system and how an engineer might approach that, modeling that. So I do want to give a disclaimer here that I am not a utility and offsite engineer, nor have I ever been one. So I'm not here to explain to you how to do your job better. You know things beyond what I know, but I have worked with a lot of these engineers in my position, as well as a colleague used to be one. So we do have good information, but take what I say with a grain of salt. And really the point is it's to give you ideas on how you can use the software in your specific case. So like I said, I'm not going to tell you how your job looks, obviously, and everyone's different. I'm doing this from the software perspective because Fathom's not an industry specific software. I wanted to kind of tie it into different industries to help people more specifically instead of generic examples. And another thing, I'm going to be moving quickly because the point is to show you that Fathom can do things, not necessarily how. Some things I will show you how to do, little tricks in the software, but for time's sake, I can't go through everything. And we have other resources to learn those things if you want to. So you'll see sometimes I show you how, sometimes I'll say I just have this ready. Again, the takeaway is for you to understand that Fathom can do things and to hopefully get you to be able to extrapolate from our examples today. So some unique aspects of utility and offsite engineering. So we'll start with definition as I understand it. Engineers involved with the utility side of chemical processes or oil processes. What that means is you are directly involved in the process, but what you are working with is not necessarily the end product money maker, and that has some unique implications. So that looks like cooling water system, boiler feed water systems, steam heating systems, and Firewater, where they're necessary for the process, but you ain't making money off them directly. And those implications then are there's little data on these systems and they're not trying to optimize them, right? So I understand, once in a while you'll be able to get a flow survey about what your system looks like, but you don't have constant monitoring and all of that, right? And you're really just expected to meet the needs of the process side. So if they tell you they need something, you're expected to do it, but yet you have little data. That makes things a little tricky, right? So as I mentioned, that leads companies to not optimizing these systems because it's not worth it. It's not worth the time. It's not the money maker. So companies find solutions that work, but not necessarily the best ones. Well, that's where software comes into play, because you don't need to optimize the system, and but you can still use software to find a better solution than what you might otherwise have found. Because using software, as we'll see today, doesn't really take any more time, especially a lot less time than doing hand calculations. So you can take what you need to, these system analyses that you would have done by hand doing the software, get better results much faster. So the two examples we are going to work through are cooling water network expansion, where engineers, as I understand it from research again in these folks I've worked with, they tend to be most concerned with velocities and temperatures moving through the system and through the heat exchangers. Velocities to ensure as little deposits as possible corrode the piping, and two, velocities are not too high to cause damage. So there's kind of a sweet spot, and we'll see that with our example. We don't want to be too low, don't want to be too high, and then temperatures, of course, to ensure appropriate heat transfer. So I've bolded velocities here because that is the parameter we're going to look at in our example. But Fathom does do heat transfer, so you can again take these concepts and apply them to other parameters like temperatures and pressures. And also, that's not to say you're not worried about flow rates and everything else. It's just this is typically the main thing you're looking at. Now with the Firewater network, our second example, people tend to be most concerned with pressures and flow rates so they can meet code and ensure, they can continue having the license to operate. And as I did in the previous example, I've bolded one of those, which is flow rates, because that's going to be the parameter we look at in our example. So it's all about ensuring you get the flow you need in an emergency. I mean, that makes sense. So though this is a Firewater network, I do want to emphasize we're not going through NFPA reporting, but rather just as if you're an engineer doing a first pass flow analysis on your system to see if we need to go further with NFPA, get reports out and all of that. There are other resources we have for NFPA because Fathom does do that, can create an NFPA report, but what we're going through is really just using the software for flow analysis as that first pass. So let's look at this cooling water network expansion. So with that, there are three topics really: calibration, expansion analysis, and then alternatives if that expansion turns out to be problematic. So here's a modification on one of our example models for our software where I have a very simplified cooling water network system here. And what we have in red dotted lines, this is going to be our expansion, our theoretical expansion. Right now it's closed, so we just have the 3 heat exchangers. And this kind of ties in what I was saying at the beginning, which is you can take these concepts and apply them to your real systems. This is a very simplified model to help you understand concepts. So what does the setup look like? Okay, what we do know, we're going to assume from an annual flow survey, is that the current system we know has about 740 gallons per minute moving through the pump. Okay, that's good to know. So we need to calibrate a new model of the current system. I need to build a model from scratch and calibrate it so that I can see that it's a good representation of reality. Then once I trust the model, I can see what happens when new lines are added so I can get accurate predictions and then answer the question, are requirements still met? Or do we need to make other changes to the system once this expansion is added? So let's go ahead and get in. So I have that same system here, displaying the pipe and junction numbers. So often cooling water networks, they're closed systems, which means there are no streams in or out. All of it's enclosed in our system boundary, if you're to look at it that way. They typically, everyone's different, of course, but they typically don't have booster pumps or control valves or monitoring. You just kind of have a pump pumping through a system, pumping water through a system to heat exchangers, and the hydraulics are purely determined, without a lot of intervention. It's just the single pump, right? So flow distribution pretty much purely on pipe resistance and then the heat exchanger resistance. And if you don't use software, in order to do hydraulic calcs, you're doing this by hand, and that's often what utility and offsite engineers will do. Well, that's what this software is for. So what I have is a model that I built with some, in here, I'm not doing any heat transfer analysis. I do want to state that. You can, again, apply this in a heat transfer situation where you do care about temperatures, but right now I'm just caring about the flow to begin with. I have a loop with water going through various heat exchangers and just kind of cycling through this reservoir. So I built it, but if we're using a standard AFT database, like this Steel ANSI, this assumes new piping, and this absolute roughness and friction we get is all assuming new pipes. Well, if we're doing an expansion on a system, that means that system has been here for a while. Maybe that's not the most realistic representation of our system. So what we see when we first build this, we run the model. I'm going to be making use of visual report in this example. What that is it's a pretty much the workspace overlaid with output from solving a solution. As I mentioned, I'm going to be going a little fast, so hopefully you've had some exposure to Fathom where this isn't all new, drinking from a fire hose. But we can see here that as is, it turns out my pump is pumping out 840 gallons per minute. And if you remember my previous slide, our real system is actually only doing about 740. So we're a little too high, and that makes sense because if we're assuming new piping, the friction is going to be a little less. That leads to more flow. So what can we do as engineers to calibrate this model to where I get 740 instead of 840? What we can do is create a child scenario, which is a copy of this base scenario. And let's see, calibration. A very useful tool for calibrating models is going to be what's known as a design factor. So if we open up a pipe, we can go into our optional tab and see this little section, design factors. What this is it's a multiplier on your pipe friction. So right now it's 1, which means whatever is in our database, that is going to be used for finding out friction and pressure drop. If we wanted to add friction to the pipe beyond what our standard database would have, we can just tack on decimal multipliers representing a % increase. So for instance, 1.1 means a 10% increase on the friction. 0.9 would be a 10% drop in friction. So using our engineering minds, we understand we have too high a flow, we need more resistance, not less. So I'm going to make this 1.2. Okay, that was just one pipe. Well, how about let's global edit all of them? I can Control A, select all my pipes, global pipe edit where all of them are selected, and then I choose what parameter I want to apply, a very specific parameter, not everything about this hypothetical pipe is going to get applied. I just want to apply the pipe friction. So the design factor. So within global edit, and there's a lot on global edit. Again, one of these things I'm going to go through quickly. Just know it's possible to change something in every junction or pipe that you have. So what I've done is now I've applied this friction extra design factor to everything. Okay, cool. So now let's rerun the model. Let's see. Okay, 795, about 800 gallons per minute. We're getting better, but you can probably already tell this is a really manual process. If you want to do it by hand, you just kind of keep iterating yourself. But what I'm going to do is I'm going to leverage goal seek and control, which is an add-on module for Fathom, which is just like goal seeking in Excel. You have a known thing you want, and then you have to vary something to get that. So in this case, I know I want 740 through the pump, and what I want to vary is all of the pipe design factors. So I'm not going to show you how to set up GSC, but I will go through it and use it. So what I'm doing is I'm unchecking the closed pipes because they're not going to matter. They don't need to be varied. So here we have a goal of 740, and we're going to vary all of these pipes design factors. Those are the basics. Say, okay, cool. So now we can run this. Oh, I'm sorry, I didn't have it, I had it on but not used. So I need to use the module. And you can see all the variables come up, and then I have a single goal. We do have webinars on goal seeking control, by the way, if you're interested. So you can see it does a few extra iterations because it's doing all this that you would have done by hand, but in the computer. So we can see our goal was met of 740, and it varied my pipe design factor to 1.487. So awesome. What I can do with this is I can create a child that will automatically put this GSC output into my input. So I'm going to say transferring GSC results. And it is what's known as a disconnected scenario. It just means it's not going to change if the parent changes, which that's no problem in this case, but you can see if I go look at a pipe, it automatically put in my GSC results. Awesome. So I can trust this as my calibrated model. What I want to do is just kind of make a clone of it. So I'm just going to say clone without children. That way, this new scenario is still going to be tied to my hierarchy, and I'm going to create another group of scenarios as I start to open this expansion. So I'm going to say open lines. So what do I need to do? Okay, I'm going to highlight these pipes. It's a little hard to see they're highlighted because I'm using the color red, and red also is the color used to indicate it's highlighted, but I know I'm highlighting them because I'm dragging right to left. Going to pipe edit. Okay, optional. I want it to be not closed. So special condition, none apply to those pipes. Bada bing, bada boom. We got to open expansion out. So there are some design requirements. We have to have some metric to see, are we meeting these requirements or not? And the way we're going to do that is through the design alert medium. So design alerts, again, I'm not going to show you step by step how to use them, but it's something that you as a user can specify so that the software will warn you if it's gone past that. So it works best with examples. We have a maximum velocity. That's one of the concerns we have with cooling water, right? So I have a maximum velocity of 9 feet per second. I want to apply that to my heat exchanger pipes. I've already created a group for that, but you can just see pipe 12, 15, 18, 25, and 27 are going to have this design alert attached to it so that if this is not met, it will warn me. And in a very similar way, you're going to go say, okay, cool. So we have 2 design alerts ready to go to watch, if anything's not being met. So I'm going to run this model, Control R, look at output, and oh no, it's almost like by design this happened. But anyway, you can see the design alerts were not met. So let's read it. Velocity is below the minimum design alert of 3 feet a second, pipe 25, and the same with pipe 27. So if I drag this over, I can kind of take a look at where those are at. I like to double click these warnings, so it'll bring me right there. So pipe 25 and 27 do not have requirements met. So let's see what they are. Let's see, there we go. So we have a certain amount of flow. Okay, 750. What's interesting is actually opening the parallel lines dropped in resistance so that the total flow rate increases, but the flow rate in each line is a little less. But 6 feet, 4, 3, little less than 3, and 2.6. So that's where we're getting this triggering of the design alert. So as engineers, again, we need to think, okay, well, how can we meet that? What are various ways we can meet these design alerts or, fall within the requirements we have? So the 3 scenarios we're going to look at are going to be looking at a larger pump. What if we replace this with a larger pump? What if we increase the local resistance in these 2 top lines right here, where these are smaller pipes? So if they're smaller pipes, well, then more flow is going to be distributed down lower because there's a little too much in this top line. And then the third one is, what if we replace, or what if we were able to insert some throttling valves in these 2 lines, or orifices would be an equivalent. So we can just kind of start there, but what do we know? We know it's a little uneven in distribution, which makes sense. As you just start to get further and further away from the main header, the flow is going to drop as because there's more length in between, more resistance. So we kind of want to take from these 2 and put them down here like Robin Hood. So the way I can do that is going to be with scenarios. So what I want to do is create a child called larger pump. Boom. And what I will do to represent a larger pump is not actually put one in, because this is supposed to be, us as utility and offsite engineers going through stuff quickly. I can model a bigger pump by just increasing the pump speed past 100%. If you are seriously analyzing a new pump, you don't want to just say this is good enough, but it gives us an idea of what things would look like if we just use a larger pump and would it work. So I say, okay, cool. Okay, go to output. Hey, no design alerts. That's always a good sign. Let's look at visual report to see what's going on. Okay, now I have increased the flow significantly. Makes sense. Velocities starting to get higher in the top line, but hey, at least I'm at 3 feet a second in these bottom ones. I still kind of have this problem of not very even distribution of flow. So just increasing the pump does the trick, but it's maybe not the most efficient. It's very capital intensive. So let's look at another option, which we're going to say HEATX pipes. So here we're going to take these and I'm going to global edit them to be, I think they are 4-inch right now. I'm going to make them 2.5-inch. Just if we were to able to replace piping and it would still be able to hook up to the heat exchanger, all pretty theoretical here. Would it work is the question. So let's see. Okay, so I've replaced those. The other ones are still all 4-inch, and these are now 2.5-inch. Okay, I have this design alert. Velocity is above the maximum. Oh, so now I've gone in the other direction. And that's why I put on that the top side of that design alert for velocity, is because, okay, yeah, I made it a smaller pipe. I made them smaller pipes, so more flow is going through the bottom sections. But by having a smaller diameter, I've increased the velocity significantly. So now I'm at 11 feet per second when my maximum I wanted was 9. So this option works for meeting minimum flow, but definitely not ideal, not what we want. It's still not really meeting the design requirements. So what if I say, let's just throw in some throttling valves. Again, hypothetically, can we cut this pipe and weld some orifices or valves in here as a localized loss point to control flow elsewhere? We're going to say yes in this example. That is reasonable. So what I can do is I can automatically bring this junction over and split the pipe, and the junction's just automatically there. So I'm going to do the same thing in this lower one. And through some testing, I know that if I have a CV of about 150 through this top line, and then a CV of 200 through this bottom one, that flow will be a little more evenly distributed. So and I can give you some reasons for why that makes sense, even if I wasn't testing too much. There we go. I just want to put it. So more flow is going through the top, which means I need to restrict it more. A lower CV leads to lower flow, and a higher CV leads to higher flow. So I'm kind of taking from here, putting a little more here, but then taking from here also and bringing it elsewhere. So let's see what that does. Also, no design alerts. Very good, good start. Let's see what's going on. So as I brought that valve in, it starts to overlap the visual report because now I have 2 pipes where there was 1. So anyway, I got to shift this around a little bit. I'm going to bring that junction there. So we can see these velocities now are a lot closer together. Okay, 4 feet a second, 3.6 feet a second, 4, 3.7, 3.2. That's a lot more reasonable. And we're starting to get closer and closer to just essentially control valves. Just with that, manual valves are going to be cheaper, but you can also think about these as orifices. Fathom does not care where pressure drop is coming from. Is it a valve or is it an orifice? It just cares that there is a loss associated with it. So we could also easily replace this valve or these valves with an orifice. So if instead you were thinking about putting in an orifice, you can have Fathom kind of back calculate what an equivalent orifice diameter would cause the same pressure drop and lead to the same flow rates. So that's this output right here. If instead I replace those valves with orifices, I can put in those diameters and I get the same results. Awesome. So that's just the first example and approach at how you as a utility engineer can use Fathom for these networks and avoid hand calculations and still have a good idea of what's going on in your system and what happens if you start expanding or do other experiments. Scenario Manager is beautiful for that because you can test many things within the same model file. Boom. Okay, so let's answer this question. Are requirements met or do other changes need to be made? As we opened up those lines, turns out we do need to make some changes. A newer pump's a little capital intensive. Replacing the new lines, maybe that it doesn't work also because there's too high velocities, but also these heat exchangers, are sized for 4-inch piping. And it seems first pass, the most reasonable thing is to insert some orifices or valves in here to redirect flow. Right, so we first calibrated the model and I showed you GSE, which is goal seek, and control to improve the process to avoid manual iteration. We opened the expansion lines to see results once we trusted that it's an accurate model, at least as accurate as we can suspect. Right? Then we leverage these design alerts to warn us or to warn me when requirements were not met. Then I can test various options that will push the system to meet the requirements. And this, too much, I'm saying requirements, too much requires. It's just, I'm asking a lot of you, I guess. But this requires understanding theory. Just because you get results, well, you have to be able to interpret results and then also kind of predict what should happen. You should have expectations, which is why we always say you need to have like engineering background to use the software. It's not just plug and play, right? Then you can choose the best one, looking at different alternatives, right? So in our example, adding throttling valves is the most viable. Okay, so that was the first example. This is the second one, a Firewater system study. What I will highlight here is smart scenario management, and then also using pump and system curves in Fathom, because it's a pretty good use. We are not going to go through NFPA reporting, as I mentioned. We do have separate resources listed here. You cannot click these links. I can. But if you do want these links, you can just email us after the webinar, or I can send you the presentation, what have you. We have a webinar in NFPA, and then we also have a walkthrough example, which is you're pretty much just reading what to do step by step, and while you go through it in the software. So again, it's more of, okay, well, we have to do a study. Utility engineers are going to kind of give it a good first pass, but then there's a scope split between the safety guys who are really going to dive in. So this is our Firewater system, where what I have is a pump pumping water from a river that's going to be at ambient static pressure, pumping to 3 different process areas in our plant. So while one process area is getting flooded with firewater, we're going to assume the other areas are closed off. That's what those red boxes are. But we have 3 areas we have to analyze, because we can't say, oh, it met the requirements of area 1, that's good enough. We have to test all 3 all the time with any change we make. And this is where the scenario stuff's going to come into play. You might ask, that looks like 4 sprinklers, Walt. Why does it say 16? I've simplified the model down to where I'm counting one of these as 4 sprinklers, which you can do in the software, and then kind of adjusting the pipe sizes to properly account for pressure loss. But it's just a simplification of the model. You can kind of wrap things in together. So the setup, there's an existing Firewater system that was confirmed to meet requirements in each process area. Oh, but that was 25 years ago. So we have to reevaluate things and see, is it still a valid safety measure? 25 years, I have no idea if that's a realistic timeline. Just take what I say with a grain of salt. That's the story here, right? Answering the question, do we still meet the requirements, or do other changes need to be made? Just like the other example. So let's jump in. Oh, there it is. So because it was an existing system, we can assume that we're picking up this model. It's already been calibrated to that original system. We can trust it as at least a representation of the system 25 years ago. So as I mentioned, we're pulling water from the river and then bringing it to these various process areas. So in a similar way with what I've done, what I did with the cooling water network, I'm going to have design alerts here. So I'm going to bring those up just to show you what's going on. So in area 1, there's 16 sprinklers. I need at least 500 gallons per minute going through the sprinkler. So what I do is I will apply it to that feeder pipe, right? I need 500 gallons per minute there. In area 2, I need 375, a little less, but still significant. I need to make sure the pump can meet me there while the other 2 lay dormant. And then in flow area 3, I need 250. It's got the least amount of sprinklers. It's the smallest process area. So I have to apply these to all of my pipes. So as I go into, you can see I've already created 3 scenarios, and it's just best to show you one by one. So as I'm analyzing area 1, the other 2 are closed off. You can see that by the dotted lines and the red squares here. As I'm analyzing process area 2, the other 2 are closed off, right? And then in a similar way, as I look at 3, the other 2 are closed off. With each scenario, I need to apply the design alert specifically, to that pipe. So again, right now we're in process area 3. That's the one open. That's the design alert that applies. It's applying to pipe 10, which is the feeder pipe here, while the other 2 design alerts are not active because those lines are closed. I'm not analyzing that. So each scenario has like its own setup, and we're going to have to look at all 3 of these scenarios every time we make a change because we have to be able to meet all 3. What we are not doing is looking at what if 2 places are on fire. Well, it's just a common assumption during safety studies that it has to be reasonable. So if all 3 of your process areas on fire, you're kind of SOL anyway. That we're not trying to design for the absolute worst theoretical situation. You're looking at like one problem at a time. So the original system has a certain pump and system curve depending on which process area we're going to. So what Fathom can do is create these what we call multi-scenario pump and system curves. Let me load it up, which is taking the system curve when I'm looking at area 1, the system curve when I'm looking at area 2, and the system curve looking at area 3, all on one graph with one pump curve because I haven't changed anything about the pump. It's the same pump. And we can see results here. So when I'm looking at area 1, I am meeting my design requirement of 500 gallons per minute. When I'm looking at area 2, I'm at about 400. That beats my design alert of 375. And then here, my design alert was 250. I'm a little above that. So this just confirms that the model, or sorry, the previous, 25 years ago or what have you, was meeting these requirements. We can see no design alerts are warning us of things. So cool. Now the question is, but we want to make changes. The best, how are we going to do that? The best way to do that is to clone with children in this case. And what that's going to do is it's going to keep all of the design alert, which scenario each design alert's corresponding to. It's going to keep all of the info, and that way I just have to pretty much clone once, and it brings across all of these scenarios so that when I make an edit globally, it's going to propagate to all 3, and I can similarly just kind of run all 3 scenarios and see what the output is. So this is a part of engineering. No one really likes it, but it requires you to make assumptions because you don't always have the data, or like you can't see inside the pipe. So how are we going to model an aged system? We could do a similar thing to what we did in the cooling water network, which is apply design factors to increase friction. But in this example, actually, what I'm going to do is assume there's 10% scaling in all of our pipes. What that does is that reduces our inner diameter by 10%, which is about 0.5 inches in diameter on the header lines, or a quarter of an inch in radius. So I can, again, Control A, whoops, I said Control S too. Cool, save my model. I'm gonna go to pipe edit, select pipe data, so it brings up this template. And all I wanna do is I just care about this ID reduction, 10%. And that one specific parameter is what I want to apply to everything. So, okay, I'm gonna scale every diameter by 10%, or reduce it by 10%. So what does that do? That's going to increase our system resistance, and it's going to lower flow rates. So the question will be, did it lower the flow rates too much, right? Okay, so because I have all three, all of those, that 10% change was propagated to all my children. I can just batch run this bad boy. So I'm gonna say I want to run the 3 process area scenarios, and it just kind of runs them sequentially. It's nice, you know, if you're doing a lot, like maybe 100 or so, go get a cup of coffee. In this case, running 3 scenarios ain't bad. And something that's cool, so I don't have to keep clicking around in each scenarios, I can use multi-scenario output, which, like the multi-scenario graph, it just kind of overlays results from each scenario. So why that's useful, this is kind of gross probably for you to see watching a presentation, can be useful if you're just the engineer looking at things. So I can see, oh, you know, it's 580 when I'm looking at area 1, it was 400 when looking at area 2, and 253. That seems odd. Let me double check that the ID reduction worked. Yes, okay, maybe I'm just crazy. Anyway, so this part is kind of gross. What we want to look at are the, oh, you know what? I'm sorry, this is why this is a problem. I have to update my definition of what scenarios I'm looking at. It's choosing my original. That's what tripped me up. I'm sorry. Again, I'm just showing multi-scenario output. How to do that, I'm doing it quickly. Just, you know, you can ask us later or look at our other resources. So as I do that, now we're getting results where I can see I'm not meeting my requirement. This is pipe 1, but whatever's coming in is coming out in each section, so I can say they're the same, right? But why multi-scenario output's useful is because, oh, cool, now I can see my design alerts from each scenario laid out on one screen, so I can see, oh, process 1, good. Process 2, not so good. We're not meeting our design requirement. Process 3, also not so good. So what I will do, let's see. Okay, what I want to do is batch run all 6 scenarios to be able to create a multi-scenario pump and system curve that's going to do all 6 scenarios on one curve, so I can start to figure out what the heck can I do to fix things. Because, you know, the question was, are requirements still met? And well, turns out no, they're not. So we got to do more engineering to figure out what the heck's going on. That little function of batch running to create this multi-scenario graph is an awesome function, because you can just kind of click the button and it will automatically generate these curves for you. The reason it takes a little bit of time to generate a curve, you can probably kind of see it picking up here, is because the model itself is at one flow rate. It kind of has to do this theoretical, like, let's see, it's the same pump. Sorry, I'll get back to my explanation here. So I'm just showing different system curves because it's the same pump. Okay, and I'm going to change this to 50 and 50, just a little formatting thing. The model itself is at one flow rate, right? But to get a system curve, Fathom has to kind of do this theoretical. What if it was at, you know, 0 flow and blah, blah, blah. So it takes a little bit of time. What we have here is how the system curves have changed over time, kind of representing that. And since we added resistance to the network, we can assume the system curve has steepened, and that's what we do indeed find. So if I start to, I'm going to turn off these. So, oh, I want my pump curve. So if we're looking at just process area 1, it went from, you know, some flow rate to another flow rate, and then process area 2 in a similar way was originally less steep, then steepened. And process 3, same way, was less steep, then steepened. It turns out, though, it was enough of a steepening that we crossed a threshold past our design alert. So the question as an engineer is, what the heck can we do? Well, we can increase our pump curve, right, so that volumetric flow goes up, or we can drop our system curve back down. Those are really our 2 options for each scenario, or sorry, for each process area. So what I want to do is, again, test 3 cases. I'm just going to make this a larger pump again. I'm going to add a booster pump to this area, which will supply flow to both because of this tie over. And a third option is I'm just going to replace the sprinklers with little larger, with larger sprinklers, if that's a viable option for you, right? Again, this is all hypothetical. So what I'm going to do is, again, clone with children. So I want to keep this kind of going, right? The three going. I want to say larger pump. What I can do is, again, model a larger pump by just increasing the speed past 100. I'm going to do 110 just to see if that works, right? Then I'm going to clone again, clone with children, booster pump. What I can do is, again, split our pipe. So I'll hold shift, bring the pump over. You can see I made them visually smaller. It's just a little booster guy, just a little pump. I'm going to enter some curve data. I've already got this ready to go, so I don't expect you just to be able to bust this out. If you're really adding a pump, again, you want to do some more serious investigation to see if this is a realistic pump. In our case, it is. Your situation could be different. Cool. Okay, so now I added that booster pump. It propagates to all 3 scenarios. Right, then I'm going to do, again, clone with children. This is going to be larger sprinklers. And what I will do is, each of these sprinklers has a fire definition of 7 gallons per minute per square root of pounds per square inch. Fire sprinklers have a different K factor than what you normally would think of with like loss factors and normal valves and all of that. Well, I want to make these a little bigger. So what I'm going to do is global edit these to be sprinkler. This could be 0, 8, and I still have 2 sprinklers per junction. Say okie dokie. I'm going to apply my loss model to all of those. Say okay, cool. And then do the same thing here. It's the exact same situation. The difference being that these are 3 sprinklers each instead of just 2. So let's go make that. Going to ambient conditions, 8, and then 3. Again, apply my loss model. Okay, so what I've done is I've set up my model in an intelligent way, where that was really quick for me to make all these various cases. So you can kind of just keep doing this over and over to test various things. I don't want to batch run 9 scenarios in front of you, not because it wouldn't take that long, but I've already got it ready to go. So I'm just going to now replace this with my pre-made model. I've changed the scenario names just to better match, which section they're under. So anyway, assume we've ran all of these and we're able to look at output. So the ideal situation, right, is the simplest fix. Is a larger pump the best idea in this case? Well, maybe. Let's see. Does it meet our design requirements, right? Do we have any sort of warnings? I can, again, go to multi-scenario. And actually what I want to do is I want to look at all 9 of them at once, just for the design alert specifically. Not because I really care about the output right now. Because that's 9 scenarios for 1 pipe. It's a lot of data to look at. What I care about is this bad boy, the design alerts, and it shows me results from each scenario. And as you can see, every single scenario that I tested, every alternative works. Cool. That's always great news. It works. Now, what is the best option? That's always the question, right? Does it make sense to replace with a larger pump? Does it make sense to add a booster pump into your system, or does it make sense to replace with larger sprinklers? In this case, I'm going to make the argument that replacing it with slightly larger sprinklers is a better option because you're going to get the flow that you need in an emergency. Is that realistic? Again, that's kind of where a scope split might occur, where the safety guys would give you reasons not to, but it's a good first pass for you to understand what's going on in the system to then give suggestions to anybody working in safety. So let's look at a multi-scenario pump and system curve that I pre-made again. So what I want to do is load up this guy again. It's the same pump because in this case, my option of replacing the sprinklers didn't change the pump. Yep, and it does that. Got to go back here. So what I'm graphing is my single pump curve and then system curves for areas 2 and 3. I don't care about area 1 because I've already confirmed that works even with an age system. So I want to kind of simplify my analysis to look at area 2 and 3, I'm sorry. So what happened? We kind of crossed this threshold in area 3, which was that it's not meeting its flow rate. By having larger sprinklers or a little less loss through the sprinkler at the end, I was able to cross that threshold. Of course, this is pretty tight, you know. It's not exactly like there's a lot of margin in this case, but it just shows you that this is kind of the maybe the direction you want to go in is start to add larger sprinklers to get that flow. And in a similar way, process area 2 went from not meeting the requirement to meeting the requirement by dropping the system resistance. Another option would have been, well, what if we just clean out the pipes? Maybe there's some solution you can pump through the system that would clean it out, and that would also work. But we've already kind of tested that because that's the original system, right? So it'd be redundant to do a scenario with clean pipes because it's already there, but that's another viable option, right? If that's easy for you. So yeah, that's how the pump and system analysis works in this case. Let's answer the question. Do we still meet the requirements or do other changes need to be made? As we saw, other changes need to be made. I know it's a shocker. I made this model for a reason, but this is what the software is good for. In a very quick manner, we can see first, trust that the model's good, experiment with the model, and then figure out alternatives, right? So the summary here is we were starting from the original system model, which we trusted to be a good representation. The system aged. So what we did was we represented this with a 10% inner diameter reduction. Again, in a similar way, you could have done design factors on friction. We found we no longer met the flow requirements for process areas 2 or 3. So, we got to use our engineering mind, right? Look at a pump and system curve to get an idea of what changes can get us to that point. Again, increasing the pump curve or dropping the system curve. It requires understanding theory. Again, I highlight this point that the software will not think for you. It just does physics and math. You have to be the engineer to figure out what you can do. So at first pass, looks like having larger, aka less lossy sprinklers in those areas is best. It seems like a fairly simple solution. Then we can pass that off, right, to safety guys to see if we'd still meet code. There's less system resistance, thus higher flows. Pass that on to them. Because if you're doing a full NFPA report, you're probably not going to simplify the model the way I did. It was just a good first pass. So that brings us to the end. Thank you for your time working through those 2 examples. Hopefully, at least something stuck out at you, gave you some new ideas on how you can use the software. Beyond webinars, right, we have other things that can keep you sharp with the software. We have a great tips and tricks blog. I really emphasize that because it's kind of hard to keep up with blogs and all of that, but they're typically really fast to read. And the thing is, if you are confused about something, almost guaranteed someone else has been, and AFT did a blog on it, which explains it in more layman's terms than like an academic paper or more technical help file, right? So it's an awesome resource. Subscribe to it, honestly, or at least to our newsletter where you get updates on the tips and tricks blog. We do have more webinars. Of course, if you go to Learning Center, you can see our library or sign up for more in the future. And then we have a awesome help file. Now with the release of newer versions, and we're stepping further into the 21st century, our help file is now online. So it's more searchable and a little more user-friendly in that way. But we have, so you can search through that. It's an awesome resource for understanding one, engineering theory and the software. But we also have walkthrough examples. So NFPA was one of them, but we have many others if you're just getting started with the software, or you just you don't think you have a great understanding, you want to do more. So again, thank you so much for your time. Here's our contact info. I'm just going to leave this up here for a bit. You can call us anytime for technical support or sales stuff, assuming during business hours here, mountain time in Colorado. Of course, you know it's mountain time because boom, there's a mountain. So just business hours, 8 to 5 or whatever, and then email us anytime depending on the nature of the inquiry. So thank you again for your time, and I wish you all the best in engineering and using software modeling. Thank you.